Well, calculus, being as big a subject as it really is, it wasn't enough to have one fundamental theorem of calculus, so we actually have a second fundamental theorem of calculus. Now, the second fundamental theorem of calculus is a little bit different, and it states that if f is a continuous function on some open interval I containing the value a, then for every x in that interval I, we say that the derivative with respect to x of the definite integral on the interval from a to some fixed value x of f of t dt will be equal to the value of f of x. Now we do have a very elegant proof of that, but let's just take this quantity here for a moment, which by the second fundamental theorem of calculus states that we should end up with the function, the derivative with respect to x of the definite integral from 1 to x of 2t plus 5 dt should end up giving us 2x plus 5. And what does that 2x plus 5 represent to us? Well, let's say that we have an area under our curve here from 1 to some non-fixed value. We've been used to taking areas of fixed intervals. But what if that interval is going to some non-fixed value x? What is there for us to say? Well, the region that we're going to get underneath this curve, starting at this point 1 all the way up to this value, not fixed value, is going to be a function of x. That is, its value will change as x changes itself, right? So that value could get larger or it could get smaller depending on how we set up our second value right here. So this brings us to the question of, well, why do we need this value t underneath our curve? Why don't we just make this all in terms of x? Well, what we're doing is we're saying on this interval, it really doesn't really matter what this value t is. This t stands as sort of a dummy variable. It's going to just take the place of our variable until such place as we've actually evaluated our definite integral. So let's just verify that this must be the case right here by taking the derivative of a definite integral. We do know. All right, so in this case, what will happen? We would be taking the derivative with respect to x of the definite integral from 1 to x of 2t plus 5 dt. So that's going to become t squared plus 5 times t, evaluated on the interval from 1 to some non-fixed number x. And that's going to give us a function. Let's see what function. Well, we're going to take the derivative with respect to x of this quantity. And this will be x squared plus 5x minus the quantity 1 squared plus 5 times 1. Well, working that out, that's our derivative with respect to x of the quantity x squared plus 5x plus 6. And sure enough, our derivative of that expression would be 2x plus 5. We could think the plus 0 right here, but essentially we don't necessarily need these in-between steps if we realize that for some fixed n value a to some value x, our derivative of our definite integral when expressed on the interval from a to x, just any fixed value a to x in that interval, of 2t f of t dt is going to give us that function when evaluated at x. Very interesting.